Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So I'm going to be telling you today a little bit about my own research, which looks deep into the very heart of matter, studying what's going on inside the subatomic particle known as the proton. So all the matter around us, the air in this room, the chairs, the floor, our own bodies, is made up of elements. Elements like oxygen, nitrogen, iron, hydrogen, carbon. And the smallest piece of an element that you can have that still has the properties of that element is an atom. An atom has its own internal structure. Atoms are made of subatomic particles known as protons, neutrons, and electrons. So on the left here, you can see a diagram of a carbon atom. So the smallest piece you can have of carbon. And it's got 6 protons, which are represented as those blue balls at the center there. And that's what makes carbon carbon. So any atom that has 6 protons, that's a carbon atom. Protons carry positive electric charge. So also at the core of the atom there, you see these yellow-looking balls. Those are representing neutrons. They're pretty similar to protons, but they are neutral. They have no electric charge. And then orbiting around outside, around this core, this nucleus of the atom, are 6 electrons. Electrons carrying negative charge. You have 6 negatively charged electrons balancing the 6 positively charged protons. So the total atom has no net electric charge, and it's neutral. So now the hydrogen atom. Hydrogen is the lightest element. It's got a nucleus with just 1 proton in it, is the most common form, and no neutrons. And it's got 1 electron orbiting around it, balancing out the positively charged proton. So how did we learn about this internal structure inside something as small as the atom? Well, it was just over 100 years ago, in 1911, working in Manchester, England, that Ernest Rutherford did a scattering experiment. He scattered alpha particles, so they're positively charged particles that come from the radioactive decay of certain heavy elements. People actually didn't even understand completely what alpha particles were at the time, but they knew that they were these positively charged particles that came from certain types of radioactive decay. He scattered these positively charged alpha particles off of a thin gold foil. And when you think of gold foil, you can just think of aluminum foil. It would just be more expensive to wrap your leftovers in. And what he found, to his surprise, was that most of these positively charged alpha particles went straight through the foil. They didn't even bend, slightly deflect. They just went straight through. But about 1 in 8,000 bounced back sharply at him. And this was a big surprise, given how people thought about the atom at the time. They didn't think of this central core with these externally orbiting electrons. They thought of it as kind of this solid lump of mixed together positive and negative charges. It was called the plum pudding model, actually, of the atom. So this was a big surprise. And what it meant was that atoms had some kind of small positively charged core, which we now call the nucleus. And to talk about the different length scales involved here. So the size of an atom is about 10 to the minus 10 meters. So 1/10 billionth of a meter is about the size of an atom. The size of the nucleus of a medium to heavy element is about 1/10,000th of that. So this is basically rounding up from this 1 in 8,000 that bounced back. There's about 1 in 10,000 that bounced back because the hard core was only taking up about 1/10,000th of the space of an atom. And then if you go to the proton, so the nucleus of the lightest element, hydrogen, that's about 10 times smaller again, so 1/100,000th the size of the total atom, or about 10 to the minus 15 meters. So these are femtometers. It'd be 1/quadrillionth of a meter the size of a proton. So to give you a sense of this, how much empty space there really is in an atom, so we're used to seeing these kind of diagrams that I showed 2 slides ago, where it doesn't look like the electrons are really that much farther out around the nucleus. But if I represent the proton as a grain of sand, and I put it in one end of a football field, right, then the electrons would be orbiting all the way in the other end zone around that grain of sand. And of course, that's only half of the electron's orbit. All right, so the other part of the electron's orbit would actually be going through the end zone of another football field put on the opposite side. All right, so I told you that it's about a factor of 100,000 between the size of a proton and the size of an atom. Right, so if you think of this analogy here, you think of a grain of sand is about 1 millimeter, 1,000th of a meter, and a football field is about 100 meters. Right, so that's your factor of 100,000. So the physics department here has been working for years to get them to convert the football stadium to metric, 100 meters, not 100 yards. But Americans still seem to be resisting converting to the metric system. So now I can try to do a different scattering experiment, look even deeper into matter, right, and try to see if there's anything inside of the proton. So this was more than half a century later. There was an experiment done in the late 1960s. It was another scattering experiment. And to get to to access even smaller things, they needed to go to higher energies than these alpha particles originally were. What they did was scatter a beam of accelerated electrons off of protons. And they found that many actually bounced back sharply. More than that, they found that they weren't bouncing off the whole proton. The way they were scattering around their target, the way these electrons were scattering, indicated that there were subcomponents inside. So protons weren't solid lumps of positively charged. They actually had some kind of constituents, something inside of them, different hard pieces. These constituents that make up the proton are now called quarks. Oh, and if you want to know about how big quarks are, we actually don't know. We don't really know how big quarks are. We don't really know how big electrons are. All we know is that they're at least 1,000 times smaller than the size of a proton. So with the demo lab here, I've worked out a demonstration for you to do scattering and try to determine what kind of mystery structure that we can't see is being scattered off of. So I'm going to accelerate my electrons down this ramp. And I'm going to look at the distribution of where they bounce off. So I'm going to scan it over a little bit. Sweep where I'm aiming. That one bounced straight back. You can see as I sweep around, they're basically going in a path like this. Let me just do one more here. And so when I swept across my mystery object that I want to know something about the structure of, I got a certain distribution of where the golf balls ended up. So I want you to pay attention or think about where they ended up as I swept across. And now I'm going to change this target for a different one. And see if where the golf balls end up looks any different, so that I can tell that these two mystery structures were different from one another. So I'll go back to this side to sweep across. One came almost straight back already. Came straight back again. Went to the other side. Oh, went back that way. So this is already looking different from what we had with the first target. Oh, that one went back that way again, even though I was sweeping this way. Oh, that way again. Oh, that one started going to that side. All the way almost at a right angle. Oop, again. And that one went on an angle in the forward direction. So did the distribution of where the golf balls ended up look different from with the second target compared to the first? Right. So let me show you now what it was. So for the second one, we have these three similarly sized sphere balls that are loosely joined together. And what the first one was just a cylinder, actually, a simple cylindrical target. So this is the idea of how we can use scattering experiments to learn about the internal structure of matter, right? We just look at the distributions of where our electrons or our alpha particles end up going, and then we can infer information, right? So if I did this a lot more, I could really get good statistics and see how things were bouncing off and try to reconstruct more and more information about the structure of the thing that I was scattering off of. So this is the basic idea of how scattering experiments can teach us about the internal structure of matter. So the simplest model of the proton is 3 quarks, 3 of these hard subcomponents inside the proton. 2 up-flavored quarks, so that's just a type of quark. People decided to call different types of quarks flavors of quarks. There are 2 up-flavored quarks and 1 down-flavored quark. That's the simplest model of the proton. But these quarks are not just sitting there free inside of the proton. They're bound together by force carrier particles called gluons. And yes, they were called gluons because they made the quarks stick together. Somebody had a sense of humor when they named these a few decades ago. Something called C-quarks are also present. These are quark-antiquark pairs that are fluctuating in and out of the quantum mechanical vacuum. And there are only 2 quarks, these up and down types, that really play a dominant role in the proton and in the neutron, actually. But we have found 4 other types of quarks, and their names are charm, strange, top, and bottom. So the strong force, I'd like to talk about the strong force. So how does the nucleus stay together? Right, one of the reasons that people had this plum pudding model of the atom, they thought that the positive and negative charges must be all sort of mixed together and spread out. Sort of in some kind of, maybe like think of a crystal grid or something, so things that are sort of equally spaced to have some minimum energy configuration. And because they said, okay, the positive charges, they should repel each other, right? People knew about electric repulsion, like charges repel, opposite charges attract, right? So you shouldn't have a lot of positive charges all clumped together in one part of the atom. This didn't make sense to people. This is what it was, though. That's what the experimental data said. So people said, well, there's got to be another force, and it's got to be stronger than this electric repulsion. Otherwise, the nucleus would split apart due to the positively charged protons repelling each other. So it's about 100 times stronger than the electromagnetic force, the strong force, and it's way, way stronger than gravity, about 10 to the 38 times stronger than gravity, thus the name. However, it's a very, very short range, so it's just about the range of the size of the proton is 1 quadrillionth of a meter, and then it just drops off really, really rapidly. So that's why the strong force really is contained within the nuclei of atoms. So what does the strong force act on? You think of, okay, electric forces act on particles that carry electric charge, positive or negative. Well, the strong force acts on particles that carry something we call color charge. Things that carry color charge are quarks as well as gluons themselves. And this is in contrast to electromagnetism. So the carrier of the electromagnetic force is the photon. And the photon is a neutral particle. It's not positively or negatively charged. So photons don't interact with each other. In the case of the strong force, gluons do carry color charge, so they do tend to interact and stick with each other, as well as interacting with the colored quarks. Why did people choose the name color? Well, because they saw that 3 different charges were needed to combine to make a neutral particle, and they thought this was analogous to red, green, and blue light combining to make neutral white light, colorless white light. So that's why they chose to call this color. So instead of having 2 things that combine to make something neutral, like electric charge, positive and negative, you have 3 things that combine to make a neutral. So we talk about red, blue, and green quarks. And so quantum chromodynamics, QCD, is the theory that describes the strong force. So chromo as a Greek root meaning color. Quarks do also carry electric charge, and I've always thought it's pretty neat. They carry fractional electric charge. So we always think of plus, number of electron charges or the equivalent number of proton charges. They exactly balance. That's sort of what we thought was the basic unit of charge. So people were just surprised to discover that these quarks carry fractional electric charge. So I said the simplest model of the proton is 2 up-type quarks and 1 down-type quark. Uptight quarks carry 2/3 of a unit of charge based on an electron or proton as a standard. So it's like 2/3 of the proton's charge. The second up quark contributes another 2/3, and then the down quark is minus 1/3. So you get the total charge of the proton as plus 1 unit of electric charge, one unit of positive electric charge, and this is equal to 2/3 plus 2/3 minus 1/3, actually. The neutron, the simplest model of the neutron is 2 down-type quarks and 1 up-type quark. So you get the neutral, the 0 total charge of the neutron as minus 1/3 plus 2/3. So one of the things that makes this a really complex and interesting area of research is something called quark confinement. So you can never see quarks or gluons directly. So if you think of the components of the atom, the electrons, protons, and neutrons, we can take all of those out. We can knock electrons out of an atom and make an ion. We can knock protons or neutrons out of an atom and work with them as beams, trap them in different kinds of electromagnetic fields or whatever. So we can really manipulate electrons, protons, and neutrons. You can't just pull out a single quark or a gluon. And so they're actually confined to these composite color-neutral particles. And we've observed, they come in either groups of 3 quarks, and here you have 3, like 1 red, 1 green, 1 blue, making a neutral particle. Everything is going to be neutral in the end that we're going to be able to see and work with due to this confinement property. And they're called baryons. It's from a Greek root that means heavy. They're the heavier particles bound by the strong force. Or quark-antiquark pairs. So antiquarks are the antimatter particle that go along with quarks. So these could be red anti-red, green anti-green, or blue anti-green pairs. And they're called mesons, a Greek root meaning middle-weight particles, so not as heavy as these baryons, like protons and neutrons. And so if you try to pull 2 quarks apart, you say, well, what happens if I try to pull a quark out? What happens is that the energy between them increases until you produce a new quark-antiquark pair, just through Einstein's famous equation, E equals mc squared. So the energy trying to pull, of the strong force, trying to pull that quark that you're trying to separate out back into whatever you're trying to separate it out from is so strong, the energy there, that it just creates a new particle-antiparticle pair. And sometimes I like to think of this as a rubber band, right? So people say, well, how can a force get stronger if I'm moving farther away? Because people are familiar with gravity. The farther away you get, the weaker the gravitational pull is. Also with magnets, electromagnetism, the farther away you get, the weaker the force is. But think of a rubber band. So right, the further apart you pull a rubber band, the stronger it's going to be trying to pull you back. Right? And then if you pull it hard enough, it actually does just split, and then you've got 2 pieces of elastic rather than 1. So it's a little bit like that. So here's the basic idea of electron-proton scattering experiment. So you'd have an electron coming in from one side, a proton coming in from the other, and you would actually be hitting one of the subcomponents of your proton, and just by measuring the scattered electron's energy and angle. So only 2 things you have to do as an experimentalist. Just be looking at, so in the golf ball case, I would have to measure the energy that they had before they stopped. Here they just stopped rolling because of friction on the table or whatever. But I'd want to know the energy that it had after it scattered, and I could measure the angle, just look at the angle around the original direction that it was going. So if you measure just those 2 pieces of information about your scattered particle, this tells you the total energy exchanged in the scattering, and it tells you how much of the proton's momentum was carried by the particular thing that you hit inside, by that quark that you actually scattered off of. So you might be asking, what does the proton actually look like? I talked about the atom and how it was lots of empty space. It had this hard core, the nucleus, and the electrons were orbiting really, really far away outside of that nucleus. And the answer for the proton is it actually depends. Depends on what kinematic regime, depends on how you're looking at it. So this is in the lower left of this diagram, so it's the sort of basic model of the 3 quarks. Right, so there'd be red, green, and blue, leading to a color-neutral particle, and this would be like 2 up and 1 down that I talked about before, these different types of quarks. So now on this diagram, the horizontal axis is going up in energy transferred, That was one of the things I said that you could learn about just by measuring the scattered electrons' energy and angle. You can know the energy transferred, so if I go up in energy transferred, then it actually, you see, it looks like there are more quarks inside your proton, but they're actually pretty spread out. It looks like there's kind of a lot of empty space, even though you have more particles. It's almost like they look like they're shrinking. So even though you have more things to scatter off of, you also have sort of more empty space, and they're not interacting with each other so much. Now, the vertical axis here is the other thing that you can learn just from measuring the scattered energy and angle of your electron. It's how much of the proton's momentum was carried by the component that you hit, the quark that you hit. So now if you go up, and so you fix the amount of energy transferred, but you look at things, you only consider scatterings that told you that the quark that you hit was carrying less of the proton's momentum. It looks like there are more quarks, and they start to look more crowded together with each other, actually. And people have hypothesized, there's a prediction that has not been tested yet, so it's actually something that I and others are working on testing in the upcoming years. There's a prediction that there comes a point, if you fix the energy transferred, and then you look at things carrying smaller and smaller fractions of the total proton's momentum, that the proton looks completely dense, right? So everything's really interacting with each other, and nothing, it looks opaque. It looks not sort of transparent anymore. Nothing would go through, everything would bounce back. But that's something we haven't actually demonstrated experimentally yet. So this is an active area of research, trying to understand sort of the complexity. So what's inside a proton depends on sort of which regime of energy and momentum fraction that you're looking at. And to show you some experimental data, so this figure on the right, again, the horizontal axis is increasing the amount of energy transferred when you perform the scattering, and the vertical axis corresponds to how much getting less and less of the proton's total momentum carried by the thing that you were scattering off of. And if you look in the bottom right of the plot, the data points all fall on these pretty much horizontal lines. And this is where they're not interacting with each other so much. This is where you have a lot of empty space, not so much gluon interaction going on. And then as you go upward in this plot, you start to see that the data points are no longer on these horizontal lines, that they start slanting, right? They start becoming these diagonal lines. And this change in behavior is this increasing gluon interactions, this increasing density, effective density of the quarks inside of your proton. So what we've learned is that there's a very complex structure in this region where the quarks and gluons each carry only a very small fraction of the proton's total momentum. And in fact, 99% of the proton's mass is generated by quark and gluon interactions with each other. So you might have heard about the discovery recently of the Higgs boson at the Large Hadron Collider at CERN, and they always talk about the Higgs boson as being responsible for generating mass. Well, the Higgs boson is responsible for generating the mass of particles like electrons, actually, but it's not responsible for generating the mass of the proton, and everything that we know of, all the regular matter in the everyday world, it's really due to the mass of the protons and the neutrons inside all the atoms in everything. So the proton is 2,000 times heavier than the electron, right? So the protons and neutrons really dominate the mass of everyday matter. And so 99% of the mass of all the everyday matter around us, all the visible matter in the universe pretty much, is actually coming from quark and gluon interactions inside the protons and neutrons in all the atoms that make up the familiar world around us. So switching gears a little bit, I'd like to talk about potholes. I'd like to talk about potholes to try to think about how different probes can be sensitive to different length scales. So I study things that are really tiny, right? And you need the right tools to be able to study something the size that you're interested in looking at. So the question is, what size potholes will bother you if you're driving a tank, right? If you go out on the weekend and do your grocery shopping with a tank, you probably won't be bothered at all by the potholes on the roads in the city, right? You probably just roll right over them. You probably wouldn't even know they were there, right? However, what might be fine driving around in your tank might cause you some problems for your car, since the wheels on your car are a lot smaller than the treads on the tank. And ones that might still be okay in your car might bother you as you're going out with your jogging stroller. Then, of course, there's a reason that the wheels on a jogging stroller are a lot bigger than the wheels on a regular stroller, right? Because if you had the wheels as small as the regular stroller, you'd have to be, as you're jogging around pushing your kid, you'd have to be worried about every little small pothole or bump in the sidewalk that you'd be encountering, and your wheels could get stuck. So the size of your wheels, right, your treads, your tires, your stroller wheels, or whatever, really determines how big potholes you're going to be able to feel that are going to bother you as you're moving along. So we use higher energies to be able to see smaller things in physics, generally. And why do we do this? So higher energies correspond to smaller wavelengths. And the wavelength is what corresponds to the size of your wheel, right? And so if you can look at different size objects by looking at different types of electromagnetic radiation, for example. So radio waves have very long wavelengths. As we get to infrared, sort of heat waves, they're shorter than radio waves, but longer than the visible light. Ultraviolet has shorter wavelengths, it's higher energy, and we can see smaller distance things if we use ultraviolet radiation. And then you get X-rays and then gamma rays. So why do we have high energy particle accelerators? Well, to step back a sec, so molecular and atomic structure of matter can be studied using ultraviolet light. The wavelengths of ultraviolet light are about 10 to 400 nanometers. When you hear a lot about nanoscience, a lot of it is studying the structure of matter at the atomic and molecular level, because nanometers are billionths of a meter are about the scale of atoms and molecules. Also X-rays, which are a little bit higher in energy, so a little bit smaller objects. You can study using X-rays. They have wavelengths of 0.01 to 10 nanometers, so billionths of a meter. But what I want to study is, remember, the proton is a factor of 100,000 smaller than the size of a single atom. So I need to go to much higher energies, and the only thing past X-rays on the previous slide was gamma rays. We don't have a good way to produce dense beams of gamma rays at these super duper high energies so that the wavelengths would be so short that I could study protons and what's inside of protons. And so what we can do is we can accelerate charged particles. So if I have an electron, anything that's charged, which has electric charge, is going to be affected by electric and magnetic fields. So I can use high energy electric and magnetic fields to accelerate charged particles to very high energies corresponding to very tiny wavelengths. They're oscillating really fast, really tiny wavelengths, so small that I can see what's going on inside of nuclei, inside of protons. So this is why we have high energy particle accelerators, to see inside them. So I work on two experiments. I'm an experimentalist. And my two experiments are the Phoenix experiment at the Relativistic Heavy Ion Collider, which is at Brookhaven National Laboratory on Long Island in New York. And my other experiment is called Sequest, and it's at Fermi National Accelerator Laboratory outside of Chicago. So the Relativistic Heavy Ion Collider at Brookhaven National Lab, so you can actually see the ring here. It's the road, actually, so people can drive around the ring, the collider ring. You can see it from the satellite image. And here's what it looks like from an aerial view, from an airplane. You can see again the ring road for the collider. So the Relativistic Heavy Ion Collider is really a great place to be studying, if you want to study nuclei, protons, and the strong force. We study a few different systems. We can have beams of protons. So we start with hydrogen atoms, we knock off the one electron, and then we've got a charged proton. It's a charged particle. It's got 1 unit of positive electric charge, and I can use electric fields, magnetic fields, to accelerate it to very high energies and steer it around in a ring. Also nuclei, we study nuclei. We knock off the electrons again. And we're also studying nuclear matter so hot and dense that the quarks and gluons are briefly deconfined. So I said that quarks and gluons can never be seen in isolation. You can't just pull them out. They're always bound together in these color neutral states, so neutral with respect to the strong force. But we have heavy ion collisions. That's why the name of the collider is Heavy Ion Collider. So for example, we collide gold atoms, or gold nuclei, on gold nuclei. And it's so hot and dense, it's actually hotter than inside the sun, but in a really, really tiny space, right? One of the order of a quadrillionth of a meter or so, that these quarks and gluons are in this sort of soup, right, deconfined from each other and not bound into bound states. But of course, then by the time they come out and we see them in our detectors, they're in these bound particles again. So we have to infer what happened at the moment that they collided. So it's a collider, so it means it has two beams colliding with each other. They're going around in opposite directions, and then each time they cross, some of the particles in the beams hit each other, smash together. And it's a really flexible facility, this collider at Brookhaven National Lab. So we can do from hydrogen, so protons, nuclei of hydrogen, all the way through uranium, we have run. And we actually strip all the electrons off, right? So they're completely bare nuclei that we're colliding. So the RIC collider, the relativistic heavy ion collider, has been running since 2000. So it's a big facility, a multi-purpose facility that's been running for 13 years now already. You can see that on the lower left of the diagram here, we start our beams over in this linear accelerator. And so they're starting just from rest, right? So first we accelerate them to just a little bit. This booster ring, if you continue along the path, gets them to even higher energies. Then there's another accelerator that gets them yet higher energies. And then finally, the beams are injected into the RIC collider, and they're accelerated to the very top energies that this machine was designed to be able to achieve. So there are two big experiments at this facility called Phoenix and Star. And my experiment is called Phoenix. So it's about 550 people. 550 of us working together from 73 institutions, so the University of Michigan is one of them, since I joined the department here in the fall. And we're from 14 different countries, or 14 institutions from 14 different countries are official members of this experiment. You can see a collaboration photo. Not everybody's there, but I'm in the middle there holding the sign. And one of the things I really like about working in this size of a collaboration is the international aspect. And this is something I hadn't really thought about before I went into this kind of science. So every day I get to work with people from all over the world, right? And we have institutions from India and Pakistan and Israel and you look at the different things you read in the newspaper about different political tensions and stuff, but science goes beyond politics, right? So people are working together every day from these countries that have animosity between them, and it really doesn't matter what the governments are doing or whatever. We're interested in working together to do the science. Also, with these large collaborations, they're really a great training place for a lot of young scientists. So over the 13 years of this facility, we've actually graduated several hundred PhD students, and I had my own beginnings. My first experience working at this facility was actually back in 1997 as a summer undergraduate student, was how I got involved. And then 4 years later, I actually came back as a PhD student. So a lot of young scientists get trained at these large facilities. And as I tell my own children, you're never too young to start learning how to think like a scientist. So here's one picture of the Phoenix detector. It's about 4 stories tall, 40 feet long. It weighs about 3,000 tons. We have different detector subsystems for measuring different kinds of produced particles or different information about those particles, such as the electric charge of the produced particles, their momentum, their energy, what types of particles they are. Here's a view from a platform on the top, looking from the top. This photo actually was on the cover of the Physics Today magazine a few years ago. So here's an event display for a gold-gold collision in the central arms of our detector. So you can see when you collide these two gold nuclei, so they have 197 protons and neutrons each. So you have 197 protons and neutrons colliding against another 197 protons and neutrons. And we produce thousands of tracks with this kind of collision at these energies. And you can see what we actually measure in the detector are basically the points, these sort of dots around here. So what we have are lots of dots where we say, oh, okay, a particle went through here, this point, went through this point, went through this point. Then what we have to do is develop computer software to try to connect the dots in the right way to say, okay, this dot here went with this dot here, went with this dot here, and this was actually a particle going through my detector like this. So what I focus on are proton-proton collisions. So these are much simpler. So I just have 1 against 1 instead of 197 against 197. So we just produce about 5 to 10 tracks at the energies I study, and it's a lot easier to connect the dots. So we don't have to worry about such a complicated problem as people studying gold-gold collisions. So here's Fermi National Accelerator Laboratory. It's outside of Chicago. So on the right there, you can just see Chicago and Lake Michigan. And circled on the left, you can see basically 2 circles for the roads. And there's cooling water, actually, also. That are the 2 accelerator rings there. So my experiment is at the Fermilab main injector, so highlighted in yellow here. And it accelerates protons, this main injector accelerator. And instead of having 2 colliding beams going around and hitting each other, it's just 1 beam, and then it hits a fixed target. So it circles around to get accelerated, and then they send it off the ring, right, and bend it around, and it just hits a target that's sitting there, waiting there. Right? And we have stationary targets of liquid hydrogen. So we have to cool hydrogen gas down to about 20 degrees above absolute zero to turn it into a liquid. And this makes it denser than if we kept it as a gas. So since our target is denser, we're more likely to hit one of the hydrogen atoms inside it than if we left it as just a gas. And we also have liquid deuterium. Deuterium is a different type of hydrogen where you don't have just 1 proton in the nucleus, you have 1 proton plus a neutron. It's less common than just having 1 proton, but it's stable. And we also have solid targets, carbon, iron, and tungsten. So this is the collider facility that I talked about at Brookhaven National Laboratory in New York has been running continuously pretty much since 2000 for the past 13 years. This is a shorter term experiment. We had just about 6 weeks of commissioning run, so sort of practice run, dry run, last spring. And we're going to take physics data starting this summer for the next 2 years. So we're actually really excited that this experiment is finally going to get into some physics measurements just in the next few months. So the University of Michigan is actually involved in the target system. So here you can see, this is on the left, you see the beam pipe. This is where the protons would come in. And you can see somebody standing there. There are no protons in there right now. It would be deadly to stand right next to the beam when the beam were in there. So they're actually installing the target system. The beams are going to come in. Here now on the lower right, this is the other side of that wall. This is where the beam would be this is the target system, actually. So you can see basically three vertical pipes. So these are 3 different target flasks, and they're on a movable table so that we can move the table over if we want to. Okay, we want to run on liquid hydrogen right now. Oh, okay, now we want to run for a minute on liquid deuterium. Oh, now we want to run for a minute on iron or whatever. And it can rotate around to get different targets while the proton beam is coming in. Here is a top view. So now what I showed you before is in the far back of this picture. So the beam is coming in from the back of this photo and hitting the target all the way at the back of the photo. And then what you're seeing here is an overhead view of the different detector systems. And you'll see that the detector actually looks pretty different from my other experimental detector. So the other experimental detector, when you have 2 equal energy beams colliding in the center, things are mostly symmetric when they come out, kind of approximately spherical symmetry, or cylindrical symmetry at least, around like this. Here we have a beam coming on a fixed target. It hits things, everything that's produced is going to fly in the forward direction. So here we have a very long detector, sort of long, narrow detector, going out to detect the particles that are produced. So where does the data go? So the experiments, so due to radiation safety, we have all of these behind thick concrete walls to shield the experimentalists, the scientists, from produced radiation when we're doing this. And we just have lots of cables running out to different electronics and computer systems. So here you can see part of the computer system where all the data goes for the Phoenix experiment in New York. So we have different, each detector subsystem, we have a couple million channels, actually, data channels coming from all our detectors. We have really a lot of cables that have to come out to bring all of our detector signals. They go into different computers to get assembled, and we look at different, we have timing information. So we know what time these signals came, and we can say, oh, okay, these all came in at the same time, so this information, this hit here from this detector, and this hit here from this detector, they came in at the same time, they must belong to the same collision. And then our collisions are about 100 nanoseconds apart here, and we say, oh, okay, these came in 100 nanoseconds later, they must be from the next collision. So as I said, we really have a lot of cables. We have the orange ones there are actually fiber optic cables that we use in Phoenix. On the right, it's a little harder to see, but there are rainbow ribbon cables that are running into this yellow rack here and coming off of the sides of our detectors. So they have the black bands are just they're just taped together into bundles, so it's a little bit easier for us to keep track of different groups rather than one by one. So one thing that I've been asked over the years by people is, how do you really know what's going on if you can't see it? In the end, you're just looking at lots of sort of processed computer information or information on a computer, right? You're not in there seeing things scatter with your own eyes. I can't just look at where my electrons go the way I could look at where these golf balls go. So with the demo lab, I worked out another demonstration. I was trying to think about what I do in my everyday life that might be a little bit analogous. And I thought, well, you know, sometimes if I want to hang up a painting or a picture in my house or anchor a piece of furniture, I want to know where the wall studs are. I don't rip out a piece of drywall, say, oh, there's the stud, and then patch it back in, right? I might knock to try to hear where the wall stud is. Sometimes I've gone around with the magnets to try to look for nail heads behind the wall, actually. Right? When I find a nail head, or when the magnet sticks, I don't know that there's a nail head. I know that the magnet sticks, but I know something about how houses are made. I say, oh, the magnet sticks there, there's a nail behind there, and that means that there's a wall stud here. So if you're doing this every day, in the construction business, you might have a stud finder. So yes, a Stud Sensor Pro, it says on it, commercial product for people in the construction business. What this actually uses to find wall studs is it sends radio waves out, produces radio waves, and it can sense different densities behind the wall. And so, let's see if I can reach from the back here so I don't block people's view. So basically you put it somewhere to calibrate it so it has a reference density. So whatever is behind the wall here, that's the density. It's going to look for differences now when I move it along. So there seems to be something of a different density here, and it seems to go vertically and around here. So I think there's going to be a stud right here where my stud finder found it. Another thing you might want to know as somebody in the construction business is where you have live wires behind your walls, right? You want to be careful if you're ripping something out with live wires behind it. So this is a device that senses electric fields, right? So you can also scan this. So it seems that there are live wires going up here, which makes sense. I've got a switch right there. It also made sense that the switch was mounted to a wall stud, so that wouldn't surprise me. It fits with the information that my instruments are giving me. So this you probably wouldn't have a reason to use in your own house. This senses magnetic fields. And you're probably not worried about different magnetic fields behind your walls, but we've set it up such that there's one to find here with this device. I think I need to stand in front. So it's sensing a magnetic field here. And this device actually tells me if it's at the north side or the south side of the magnetic field. So it was lighting up red there. So it's sensing the north side of a magnetic field at that point behind this wall. Now, hopefully you're also not looking for radioactive sources behind your walls, but I've got a Geiger counter here. So Geiger actually, as a young scientist, worked with Ernest Rutherford in Manchester. So he's actually the one who did the original scattering experiment that Rutherford's famous for. So we can, so first, we hear a few clicks. There's cosmic radiation, actually, cosmic rays. So you hear an occasional click. Cosmic rays are coming from outer space all the time. A lot of them don't make it all the way through our atmosphere. A few of them do. So actually, one of the high radiation jobs is being working in the airline industry as a flight attendant or a pilot, because you don't have as much atmosphere to protect you as you do working at sea level. So we hear a few clicks, but not so many. So let's see if we can find anything behind our wall. Seem to have radioactivity behind this point in the wall. And I'd like to show the people in the front row that I'm not irradiating them, actually. So there's an awful lot. So you guys just stay. So then the last thing I'd like to show people is I've got an infrared camera here. And infrared cameras sense infrared waves, which are basically heat waves. You can think it's the wavelength that gets emitted by everyday objects, just that we're not absolutely cold. So we're emitting these electromagnetic radiation, we're emitting infrared waves. And so I'm going to turn on the switch, which is going to complete the circuit. And when electricity passes through things, it can heat them up. And if you look, you should look at the wall and you should look at the image. And we're not going to see any changes if we just look at the wall, right? But we're going to see something with our instrument that's sensitive to heat. And we can see that there's actually a Michigan M getting hot behind the wall, even though we can't see anything with our bare eyes when we just look at the front of the wall. So now if I turn this all around, you guys can see if all of my instruments were actually correct. So here was my wall stud next to the switch. Here are the electrical wires going vertically next to the stud up to the back of the wall switch. Here's my magnet. Remember I said my magnetic field sensor told me that it was at the north end of the magnet over here. Here, now it's green, which means it's the south end. I'm on the opposite side. Here's my radioactive source in this bag. And here is my M wrapped in coils that got heated up when I flipped the switch. So just to summarize, even though protons are a fundamental building block of everyday matter, we still actually have a lot to learn about the complex behavior of the quarks and gluons that are inside them. High-energy particle accelerators allow us to probe the structure of very tiny objects. And there's a community of a couple thousand of us around the world working to unravel the mysteries of the proton and the strong force that holds it together. Thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the physics department, and by gifts from friends of the program.